We'll open this up in a couple of days, and we'll let you know what we find. So, a lot of foam. Woohoo! What is this? This is... Well, hi boys and girls. Today we're going to talk a little bit about motors. Not the kind that you normally see with traction motors, but we're here with Tracy McSheery, and what we're going to be talking about today a little bit is wheel motors. Now there's several of them out there, but this wheel motor is a little exciting because basically it's reverse to what we would normally see in a wheel motor. And so with that, I'd like to introduce Tracy. And Tracy, could you maybe just introduce yourself a bit and the product?
Sure. My name's Tracy McSheery. I'm a mechanical engineer with Sapphire Motors, and we're reinventing the wheel because that hasn't been done enough in the last 10,000 years. And along the way, what we found out is some of the people before us have done a really good job, and that has really laid the groundwork for us to push it to the next level. And as part of that, I was doing some research, and I found out these guys from Lean Design had already done a lot of the skullduggery and heavy lifting for how things are done. So when I watched that video, at the end, Sandy almost injured himself playing with a bunch of magnets. And having done that before and having the scars to prove it, I commiserated with him and sent him out a toy that we had built as we were learning about Hullback arrays.
Okay, so see the end of that finger and the side of this finger? Yeah, that's what happens when you screw around with magnets. And even if you're careful, they bite. But I was using ordinary types of magnets, but what Tracy's got are Hullback Array magnets. And some of you saw that I opened up the box, and inside the box, after you pulled out the foam and everything, was this wonderful little product right here. And what we're looking at here is a Hullback array that Tracy sent us. So Tracy's going to give us a little exercise or education, I guess would be a better word, on how this thing actually can work. And he's got tons of little projects already going, so he's going to talk to us about how it works and maybe show us one that he's got at his fingertips. So the one thing is, you can see I can move it a little bit, and if I was really stupid, I would try and pull this apart. I probably could, but I'm not sure whether I could hold it apart for any length of time. So this is the little demonstrator that Tracy sent me. So you want to jump right in there, Tracy, and
Sure. About 30 years ago, a gentleman at Lawrence Berkeley Labs named Klaus Hullback realized when he was trying to make a squiggler for the linear accelerators that he could take an array of magnets, and instead of just having them north and south like we're all used to in magnets, he actually added some east and west facing magnets and found out that what happened is they summed on the top and they negated each other on the bottom. So you ended up with what was called a one-sided magnetic array. Now, the interesting thing about it is, like most inventions, there was actually another gentleman that found out that about 10 years earlier, wrote up about it and decided, well, who cares? There's nothing you can really do with that, because he was looking at magnetic tapes at the time. And then when I learned about it, a gentleman at Lawrence Livermore Labs, Dick Post, had started to work on magnetic bearings and other clever devices. So a lot of people have worked on these Hullback arrays over the last 30 years. And one of the groups was at the Commonwealth Research Lab in Australia, the CSIRO. And they took what Dick Post had done and what Klaus Hullback had done, and they put it together, and they arranged a motor, a pancake motor, as opposed to a typical can motor. And at the time, if you remember, brushless motors were still kind of a new thing. So the electronics often cost more than the motor. So you could get a motor like this that was a brushless motor that would cost a couple $1,000s because the motor controller was $5,000. And only in applications where you could justify that $10,000 were people using these brushless motors or these pancake motors with brushless controllers. Now, fast forward 25 years, and now the controller can be made for about $50. If you haven't watched Sandy's other videos, you'll find out there's a difference between what it can be made for and what it sells for. Henry Ford found out the same thing 100 years ago. Bottom line is the brushless motors are a good idea. They're more efficient, they're less noisy, there's all sorts of wonderful properties with brushless motors. And what our friends at the Commonwealth Research Lab, or I'll just say CSIRO or CISRO, came up with, is to say that if we arrange the magnets instead of along this axis, we arrange them radially, then what ends up happening is we get a very compact motor configuration. And if you're trying to make an in-wheel motor, if you're trying to make a compact device, they demonstrated over 25 years ago that they could win half the solar races with this very efficient, very nice compact design. They won half the races. Minor detail, that means they lost the other half of the races. And so what we did is we just talked to them. Well, we did some research and we found out why they lost. And they're for obvious reasons. The insulation tended to overheat. A lot of people couldn't afford them. They were $10,000 a piece. So again, we looked at it and said, well, why? But the key thing to recognize is there's no magic in this design. If you're willing to make this, so you've got a magnet that's about this long here, and then on the other side, you've got a second magnet. And then together, like the array, can you hold up your Hullback?
Yeah, we're just about.
That's actually two Hullback arrays there.
Yeah.
And they're face to face.
Can you see it a little bit?
The magnetic field is so strong that if you tried to rotate those, you would potentially hurt yourself because it would take on the order of 100 pounds of force just to get to skip a magnetic tooth. So those two Hullback arrays are face to face. And that's actually the field that the coils that go in between have to overcome. And the nice thing, that's a nice configuration. Now, as long as you recognize there's two magnets in there, it's effectively would be equivalent to a CAN motor that was this wide or long, if you will, for a regular radial flux motor. So these are compact and powerful, but as soon as you can go longer than this 2x, the CAN motor, the normal motor, starts to win. But the nice thing is, in many applications, you have more room radially available. And so now you can take advantage and stretch this out. Now that does a couple of interesting things. That if I increase the diameter, then the moment arm, which is roughly at the center of the magnets, goes from this long to this long, and that doubles the torque. And then if I made it this wide, then the perimeter is also doubled, so I can put in more spokes or more magnets, if you will, and that doubles the power. And then if you're going to go ahead and make this long, instead of the magnets being 1 inch long here, they can be 2 inches long out here, and that also doubles the force, which doubles the torque. So what ends up happening is by doubling the radius of this motor, I actually get 8 times the potential power output. But I still use the same amount of bearings and the same amount of shaft and other things. So the goodness, the power density of these motors tends to be a bit higher than the standard radial motor that you see everywhere. There's well over 500 million motors out in the wild, pumps, compressors, industrial applications, HVAC systems and such, and they tend to use these regular radial motors. But what we think is, in many cases, these axial flux motors are a much better fit in terms of efficiency. But again, now that the motor controllers are affordable. So it's not just the fact, the motor's been around for 25 years. It's the advances in the electronic controllers and the MOSFETs that have really enabled this as much as the magnetic design.
Yeah, so I'm very, very interested in this because we have 2 and now 3 and maybe 4 different little cars, so 3-wheel vehicles. And for them, the traction motor is not as appealing as what it would be for a Tesla or a Porsche Taycan or something like that. So these types of motors, the wheel motors, are very, very handy for the type of product that we're developing right now. So I'm very interested in all this stuff, and I'm interested for two reasons. One, because I'm an engineer and I'm kind of curious about that stuff. But even more than that, I want my customers to have the absolute best product that they can get their hands on, and that's why I was so excited when Tracy came along and told us about it, because I've been a real fan of the Hullback effect for a long time, ever since I found out about it. Do you have something where you could show that, like an illustration or something?
Well, there's on the Hullback, there's a wonderful Wikipedia page that describes both the arrangement of the magnets and stuff. So we might later on, if you can, superimpose the image from the Wikipedia Hullback page on that. For the motors themselves, if you look at any motor power diagram, what you'll find out is that there's a famous phrase attributed to many people, but basically it says that horsepower sells cars, torque wins races.
No, that's a very accurate assessment. And having been I raced cars, and I can tell you for sure that even though, like, I raced a thing called a Morgan Super Sport, and there were plenty of people that were quicker off the line than what I was and whatnot, but I'd always managed to catch them. And as soon as I got in the right gear, and we could get around the corners, my little, as some folks quaintly refer to it as my tractor motor, as in something you pull discs and plows and whatnot with. As soon as I got that going, I had more torque than everybody else, and I could get out of any situation and leave them in the dust. And that's why I won quite a few times. Not because of my excellent driving skill, but because you had to wait until you could get to the point where you could actually utilize that torque, because every normal ICE car has a torque curve, and you want to try and optimize where you know you're going to get the best efficiencies. The difference here is this is electric, which means that I got torque all the time, pretty much the same torque. There is another term that's loosely put out there called peak torque, but it only lasts for like 30 seconds or 20 or 30 seconds, and then it's back to whatever you've got. So I'm very interested in this, because I believe that as we move out, we can get exponentially more torque in our motors, and that's going to make the people that buy the cars we design a lot happier. Yeah.
Well, those are all spot on points, because normally what happens is your motor, whether it's an internal combustion engine or an electric motor, is driving a gearbox or transmission. That gearbox or transmission is only 80 to 90 something percent efficient, depending on how much oil you're moving around and squishing through the gears and stuff. So even if your motor, let's say it's a nice electric motor and it's 95% efficient, if you go through an 80% transmission, you're down into the 70%. And so if we can eliminate the transmission or go to a direct drive gear that's, let's say, 98% efficient for that gear, now we have more torque to the tire. And that's really what it's all about. It doesn't matter how much torque your engine produces if it doesn't actually reach the pavement.
That's correct, yeah.
Again, the wonderful thing about the high power electronics that are available now is they can deliver as much power as your battery is capable of putting out safely. And for the 0 to 60 in 4 seconds, we only need that for 4 seconds. If you don't overheat the coils so that the resistance goes up, you can put in huge amounts of current during that time. And what we've been developing at Sapphire is a way to take advantage of the fact that for, let's say it's a putt-putt and it takes 6 seconds. Well, we still only need to overheat the motor for 6 seconds. And if we're going to put 4 of them on 4 different wheels, well, the good news, bad news is now we've got on the order of 1,000 horsepower. Well, we don't need that for more than 6 seconds, because you're going over 120 miles an hour in that 6 seconds. So again, the amount of time that we need to put that power from the battery directly to the pavement, going through the motor and the gears and whatever, is a very short amount of time. And we need to design the electronics, the shaft, the gearing, so that they can handle that. Now, one of the advantages that you just kind of alluded to is the internal combustion engines tend to have a sweet spot that's very narrow. And then you have anywhere from 2 to 16 gears if you're a semi-truck to be able to move that sweet spot with the gears, whereas we can actually do that electronically. And so what that means is that we sacrifice a little because we're only operating. Let's say your tire is spinning at 750 RPM on a 32-inch wheel going 75 miles an hour. That means that the motor, if it's direct drive, is spinning at 750 RPM. Well, you get twice as much power with the same torque at 1,500. So the good news is by adding a gear, we can double the power. But at a certain point in time, if we have enough torque and we don't lose that 3% through that gear, we're better off with direct drive. And then we have a lower weight because we don't have that gearbox, that transmission. And then we have less components that have to be lubricated and maintained. So you get a snowball effect with simpler systems, lighter cars and stuff by making it direct drive. And then you also have an advantage in that you can do tricks like a electronic differential so that you can be maintaining the steerage and stuff. If you start getting in wet pavement and hydroplaning and such, you can correct for a lot of these things electronically thousands of times per second, again, with advanced electronics. So we're really trying to take advantage of the microprocessors, the high-powered switching electronics that Cree, International Rectifier, ST Micro, and others have all developed, and say, let's not just think of a motor in terms of wires and magnets. Let's think of it in terms of solving what the driver needs, and that's to turn the ignition, put the foot to the pedal, and then the vehicle starts moving with as much efficiency and as much reliability as possible.
And that's the point that really I'm trying to make with the three-wheel vehicle. Everyone says the same thing, including Elon Musk. Well, these things are not safe. It's not from crash worthiness and whatnot. People are worried that we're going to get a Robin Reliant that rolls over.
The Top Gear video was hilarious, but it was intentional.
Yeah, and how do I get rid of that problem? Well, anti-roll control would be one, but the other one is if I can control the wheels, if I can control their spin, guess what? You'll never turn that thing over, never. And that's kind of why I want to go with the wheel motors. I want each individual wheel to know that it has to keep the car on the ground. And so with the Nobe, for those of you who looked at that video, you can see in the video, the guys are doing donuts, okay? They're drifting and whatnot. How did they make that happen? Well, that's by having three wheels that are all moving. All of them are powered, I should say. And by using your controller, you can keep the car from flipping over, spinning out. The driver has complete confidence and complete control in the vehicle. Hence the reason that torque is so damned important. And anybody that knows anything about how to go fast, there's really, if all things are equal, the guy with the least amount of weight and the guy with the least amount of friction is going to win. And so if I can get rid of friction, like gearboxes and stuff like that, and I can get rid of weight because a gearbox, again, weighs something, I'm pretty happy. And then I'm getting rid of an extra wheel. I only got three wheels to deal with to get me where I want to be instead of the four. And I think that with all the electronics and whatnot that we've got right now, plus the use of wheel motors, good wheel motors, at a good price. That was a hint. I know.
Well, you get the friends and family discount.
Woohoo! I'm happy about that. But anyways, if we can make all these things come together in a good way, we've got the brand new wheels as in plural. So
let me point out something that you mentioned earlier that I think bears repeating here, is that by moving the box around where normally the engine in the Robin went and stuff, and moving it to batteries much lower, that lowers the center of gravity by a huge amount. and then lowering that center of gravity is going to make it much, much more stable than anything before.
And the other thing that we're going to be doing is we're putting in air suspension systems, which means that I don't care about spring deformation and whatnot. I tell it, this is where I want you to be. So no matter what, if the road is up here or down there, those air shocks are just going to, the air suspension is just going to move it so it's flat. So the car will be flat. Maybe the road's like that, but the car is going to be flat and it's never going to be sliding off or blowing away. What we have to do is, in every situation, doesn't matter whether it's a rocket ship to the moon or just trying to make a bicycle work better. Everything is just a math problem. And if you can solve the math problem, you get rid of the quality issues, you get rid of the safety issues, you get rid of every issue you've got. All you have to do is think about it as a math problem, and everything becomes easy. And that's why I like this. This is just another math problem that is going to be solved by making it bigger in diameter.
It's geometry.
It is.
Yeah, and that's why, like I said, I think it's important to give credit to Dick Post, give credit to the CSIRO people who developed this, to all the people who've tested it over the last 25 years, and then to recognize that it's the confluence of batteries that are powerful enough to be able to give you the 240 volts at 100 or 200 amps to impress people. So the battery chemistries and the battery manufacturers are equally as important to the motor controllers and equally important to what we've done to make the motors affordable. It's the combination of these three things, not just any one.
Right, and every once in a while you come to a confluence. So you bring together the motor, the batteries, and basically the need to, I never thought I'd ever say this, but save the planet. I mean, at the end of the day, we've got to do something about what's going on. I never really got onto the bandwagon for the ecology and whatnot until I went to China. And when you go to China and you look at Hong Kong, and you look not so much at Hong Kong, but Beijing or Shanghai or any of the areas where there's steel mills and they're trying to generate electricity with gigantic coal-powered operations, it suddenly becomes painfully obvious that this is the wrong way to go. And I mean, over there, I had customers who had kids that were buying. This is no kidding. They were buying little bottles of oxygen that somebody in Canada was taking mountain air. So they were taking the air from Jasper. It's a park in Canada, in Alberta, and they were pumping the air into this and then selling it in China for an outrageous price. And so you came home and you plugged your kid into this thing and they got a chance to breathe mountain air. That's telling, you know. Something's wrong when you're doing that kind of stuff, and accepting it. People were accepting it. So I think that what we need to do is we need to look at this confluence, look at the electric motors, the batteries, the inverters, the inverter converters, the new styles of electronics and whatnot, and try and figure out how we can, like I say, redesign everything. Now. One of the things that I got I don't know, negative Nelly said, well, how are you going to do that with a gyroscope and all this stuff? Well, if we wanted to look at a gyroscopic car, we could look at the Woolsey, okay? And the Woolsey gyro car was made in about 1912 to 1914. It seats 9. It only has 2 wheels. And it runs on a 25 horsepower motor, gas engine, obviously in those days. So when you look at that and you say, oh yeah, we've come so far. And I see that, and I see it standing there, sitting there, 2 wheels with 8 guys in it, or 7 or 8 guys, I can't remember. And I have this picture, by the way. And they're all sitting there in their little bowler and top hats and bowler hats and whatnot. And I'm going, Huh? And we can't do better than that. So I think that the Confluence is going to come together. Sure, I mean we're going to have this this three-wheel car, and I bet you anything if I said I'm going to make a two-wheel car like the Woolsey guys did, I'm sure there'd be people telling me, oh, that's not going to be safe. That's going to be terribly unsafe. But at the end of the day, if somebody's already done it in 1914, my guess is that we could probably try and figure it out and do it in 2020. So it has been a few years since that car was out.
Yeah, I don't even remember that one.
You don't? I'm glad to hear that.
The 1920s are a complete blur to me.
Really? Oh, well, there you go. I remember them vividly, so there you are. Yeah, but I am older than you. So, but at the end of the day, I think that what we're looking at here is a new kind of revolution, and I think that we need this car, and we need these types of cars, and we need this type of electric motor. Tracy, this has been really informative. I love this product. I like the way it looks. I like the fact that you're using the Hullback effect. And what I'd like to do now is I'd like to give you the last word so that you can tell the world whatever we haven't told them so far. Bring it up and let us all know. We're all ready to be enlightened. So Tracy, it's all yours.
Well, I think all the car companies, Tesla and GM and Toyota and stuff, are actually heading in the right direction. There's over 1 billion cars in the world, and there's over 300 million delivery vehicles, trucks, and buses. And in many cases, the more power they use, the more advantage they're going to have, the more money they're going to save. We've done some calculations that have said that a semi-truck typically goes about 600 miles a day, and they get about 6 miles a gallon in diesel. So that means they're burning about 100 gallons of diesel a day. So if they convert that at $2.50 into what it would cost if we electrify that semi-truck, it turns out that they'll actually start saving money in 2 years. And then by 12 years, they'll have saved about $500,000 in fuel and maintenance costs. So we're not going to go green just because it's a good idea and it's better for the air, as you were saying. We're going to go green because the accountants are going to say, hey, you're saving me $500,000. Now, for a passenger car that only goes 60 miles a day instead of 600 miles a day, it takes longer, but it's still clear that with improved batteries and improved motors, that there's an incentive for everybody to switch, especially if we end up being able to buy the electricity at night from, say, 11 p.m. till 5 a.m., when it's 1 or 2 cents per kilowatt hour, to encourage people to do that. So the good news is, by adopting the latest technology, we're actually going to help make the air clear everywhere, whether it's with my motors or anybody else's motors. It's the combination of the motors, the controllers, and the batteries that are really going to help us.
And I couldn't agree more. There's always going to be the right tool for the right application. For me, looking at these three-wheel vehicles right now, I think the wheel motor is the right tool, and I'm going to be progressing down that line. So with that, what I'd like to do is thank you so much. Thanks for filling us in on this. Yeah, because it's information that we all should know about and should examine. I mean, it's always good to make sure that what we're doing is the right thing. So with that, thank you so much for coming on to Munro Live. And I'm hoping that we're going to be maybe one of these days seeing each other in person.
That'd be nice.
Yeah, it would be. So thanks so much.
Take care, all.
Bye-bye. Bye-bye.